Welcome to today's Explainer. Today, we are diving into something absolutely fascinating. We're essentially pulling back the curtain on the invisible engine that runs, well, pretty much our entire modern digital world. You might not see it, honestly, you might not even know its name, but it is the foundational architecture dictating how your most important daily tools function. We're talking about ARM architecture. 230 billion. Yeah, you heard that right. Since at least 2003, over 230 billion of these ARM chips have been produced. To put that completely staggering figure into perspective, that is roughly 28 chips for every single human being currently living on Earth. It's an absolutely massive scale of manufacturing and deployment that almost defies comprehension.
So you got to ask yourself, right, what exactly is powering your digital life? Where are all these billions of chips actually going? Well, this massive manufacturing number connects directly back to the smart devices you're probably using right at this very moment to follow along with this explainer. This invisible giant is sitting right there in your pocket, on your desk, and in your backpack.
Okay, let's dive into this. Section 1. Defining ARM architecture.
Here's the really crucial distinction we need to make right off the bat. ARM, which is usually stylized in lowercase, isn't actually a physical chip itself. Instead, it's an instruction set architecture, or ISA. Specifically, it is a family of RISC architectures. That stands for Reduced Instruction Set Computer. Think of it not as the building itself, but as the foundational set of rules. It's the underlying grammar and vocabulary that dictates exactly how software communicates with and controls a processor's hardware.
Now, understanding this unique business model is a total game changer. We have ARM holdings on one side and hardware manufacturers on the other. It is a brilliant intellectual pivot. See, ARM Holdings doesn't fabricate the silicon you hold in your hand. Not at all. They develop the instruction set architecture and design the cores that implement it. Then, they license those blueprints out to other tech companies. Those partner companies are the ones who take the blueprints and actually build the physical devices.
Section 2. The secret to ARM's success.
It all really boils down to a crucial trifactor of success. We are talking about low production costs, low power consumption, and low heat generation. When you're trying to build consumer electronics, this combination is literally the holy grail. You want it cheap to make, you want the battery to last all day, and you definitely don't want it burning the user's hands. These three traits combine to make ARM the absolute perfect choice for the mobile technology revolution.
And because of those specific low power and low heat advantages, ARM became the undisputed engine for light, portable, battery-powered devices. We're talking about the smartphones we check 100 times a day, our laptops, tablet computers, and incredibly vital embedded systems. This is exactly why ARM beat out the heavier, more power-hungry competition in the mobile space. It was just the right architecture at the exact right time for the mobile boom.
Section 3. Decades of architectural evolution. Let's track how this actually evolved. Generation 1, the original ARM1, had a 32-bit internal structure but a 26-bit address space. That bottleneck limited it to a mere 64 megabytes of main memory. I know, right? Tiny by today's standards. That massive limitation was finally removed in the third generation, ARMv3, which introduced a full 32-bit address space. For several generations up to ARMv7, the architecture just remained 32-bit. But the massive paradigm shift? That happened in 2011. That is when the ARMv8A architecture was released, introducing a 64-bit address space and 64-bit arithmetic with a new 32-bit fixed-length instruction set. That basically opened the floodgates for modern computing power.
Now, what's really interesting about this is how highly adaptable the architecture is for different computing roles. ARM Holdings continually adapts to specific needs through extensions. Take Thumb, for instance. By adding both 32 and 16-bit instructions, it drastically improved code density. Then you have Giselle, which is an extension designed specifically for the direct handling of Java bytecode, creating some highly specialized software efficiency. And more recently, they've added SMT, or simultaneous multi-threading, which allows for vastly improved performance or fault tolerance. It's like a toolkit that can be customized for almost anything.
Section 4. From phones to supercomputers.
This extreme scale brilliantly illustrates the true flexibility of ARM. On one end, we have its humble roots, pocket-sized efficiency powering embedded systems and smartphones on tiny batteries. But on the other end, we have massive scale computing. ARM processors are increasingly being used for full-fledged desktops and massive enterprise servers. Get this, ARM architecture actually provided the computational heart for Fugaku, which reigned as the absolute fastest supercomputer in the entire world from 2020 to 2022. It literally scaled all the way from your pocket to the pinnacle of global computing power. So that brings us to the future. ARM is unequivocally the most widely used family of instruction set architectures on the planet. Its dominance is only increasing every single year as its blueprints get adapted for more and more powerful devices. So knowing how integral it is to the very fabric of our modern world, the ultimate question is this: what exactly will the next 200 billion chips power? Thank you so much for joining me for this explainer. I really hope it sparked your curiosity to look a little closer at the invisible rules running the devices you touch every single day.